This tutorial is going to be about subsection 2 out of ideas to implementation, and there is the dot point right at the end, dot point 6, which says identify the relationships between photon energy, frequency, speed of light and wavelength, E equals HF and C is equal to F lambda. Now, unfortunately, what's not explicitly mentioned here in the syllabus, or really anywhere else for that matter, is that within this dot point is wrapped up this other concept called electron volts, which is something that you absolutely do need to know about. And even though it's not explicitly there, in fact, if you go looking around, the only point that you're ever going to find any mention of electron volts is here in the data sheet that you get at the back of your exam, where you've got this relationship here, 1 eV. Now, eV is the symbol for electron volts, is equal to 1.602 times 10 to the negative 19 joules. So really what electron volts are is that they are an alternative unit of measure for energy, and they're typically used for energy values that are very, very small. For instance, the energy of individual photons. An individual photon on its own doesn't carry much energy, so you end up with these energy values that are very, very small, times 10 to the minus 14, typically for photons in the visible light part of the spectrum. So those numbers are kind of ugly to work with, but if we convert them into electron volts, then they're a little bit nicer to work with, and there's a couple of other little neat shortcuts that electron volts allows you to do. The remainder of this question is going to be talking about using electron volts within the context of question 26 out of the 2014 HSC physics paper. And look, it's an absolute bastard of a question. It's easy when you know how it's done, but if you're there on exam day and you're not really familiar with electron volts, yeah, the chances of you doing well in this question are pretty slim, but we'll go through it anyway. All right, so let's write this out again. 1 eV, or 1 electron volt, is equal to 1.602 times 10 to the negative 19 joules. And before we go any further, it's worth going back to the Year 11 course and just briefly looking at the definition of voltage. So if we remember that 1 volt is equal to the amount of work done per 1 coulomb of charge, well, what about if we replace the charge not with 1 coulomb's worth, but just with the charge of 1 single electron? So in this case, we're going to take this formula here and replace Q with QE, the charge on the electron, which is negative 1.602 times 10 to the negative 19 coulombs. So hopefully you should see now that this number here and this number here has got the same magnitude. All right, so what happens now is that we're just going to rewrite the formula out where we have the volts is equal to work done by 1.602 times 10 to the negative 19 coulombs worth of charge. Multiply that across there, and this is going to give us the electron volt. Okay, so in this case, the work done, because if we have 1 volt, then that takes a value of 1. So 1 volt multiplied by 1.602 times 10 to the negative 19 coulombs. You'll see that we've taken off the negative sign here because it's not needed. And this is going to give us an amount of work, in other words, work in joules. So 1.602 times 10 to the minus 19 times 1 is 1.602 times 10 to the negative 19 joules worth of work. All right, now the definition of the electron volt isn't so critical to using it under exam situations. So let's have a look at the question and we'll go through it step by step, and when it comes to dealing with the electron volts, we'll cross that bridge when we come to it. Okay, now question 26 is in a number of parts and it's worth 5 marks total. Now let's do part A first. It's reasonably straightforward and it's worth 2 marks. However, it is a two-step solve. We want to know the energy of the photon, and the only information we've been given is the wavelength. So you can probably guess that you are going to have to use E is equal to HF to solve this. But at the moment, we've got two unknowns, the energy and the frequency. H is the Planck constant, and we know that value. So we need to get the wavelength in nanometers and convert it into a frequency. And we can do that by using C is equal to F lambda. So at the moment, the lambda that we've got is 415 nanometers. But because this is nanometers, I can't put it into the formula. It's got to be in SI units, so we need to convert it to meters. And for nanometers, it's really easy to do. 415, okay, for nanometers, it's always times 10 to the negative 9 meters. All right, I'm now going to run this through C equals F lambda. C, of course, is the speed of light. So 3 times 10 to the 8 meters per second is going to be equal to F. That's what we want to find. And lambda in meters. 415 times 10 to the minus 9 meters. Okay, it's time to grab your calculator out, and this will give you a frequency of, we're just going to take the speed of light, 3 times 10 to the 8, and divide it by that wavelength, 415 times 10 to the negative 9. And this gives us a frequency of 7.2289. The next digit is a 1, so we might just round off there, times 10 to the 14 hertz. And typically, frequencies of photons in the visible light part of the spectrum, by the time you do these a few times, you start recognizing that they're in this range of 10 to the 14 hertz. It's a very high frequency. Now I've got a frequency, I've got the Planck constant, and so I can run it through E is equal to HF. So E is equal to H. Now at this point, we're going to sub in the Planck constant, 6.626 times 10 to the negative 34 joule seconds, and the frequency 7.2289 times 10 to the 14 hertz. Now, when I put this through my calculator, I've actually already got the unrounded version of the frequency sitting there, so I'm just going to run with that. What's on my calculator? I'm just going to multiply it by Planck constant. So 6.626 times 10 to the negative 34, and this gives me an energy of I'll write out exactly what's on my calculator, 4.789879518 times 10 to the negative 19 joules. That's a bit of an ugly number, so we're going to round off just to a few, maybe 1 or 2 sig figs than we need to here. But you'll see that all those digits, basically, until we get to the 1 right at the back, are all 5 or over. So let's round off like so, 4.789, let's just leave it there. Not joules yet, it's times 10 to the negative 19 joules. Okay, now if you were to write that as your answer, you would get the marks. You've calculated the energy. I would believe that the Board of Studies, or NESA, whoever they're called now, would accept an answer written either in joules or in electron volts if you wanted to convert that energy into electron volts. Either way, we've answered the question. Okay, let's now look at part B. Right, moving to part B, and the first thing that you get in part B, unfortunately this question is split over two pages for some reason, so we're going to have to look at each little section one at a time. Anyway, in this section you do or in this part of the question, you do get a diagram that shows you a photocell. And there is a critical bit of information here where you've got a power source down the bottom supplying 4.1 volts. And you'll see that the positive terminal here is connected to the collector, in other words, the anode of that photocell. So we have negatively charged electrons moving off the aluminium surface and heading towards that positive collector. So at this point, judging by the picture, those electrons have popped off the surface of the aluminium metal. And for electrons to come off the surface of a metal, they've got to get enough energy. And there are three ways in which you can give those electrons energy. The first one is heat. And this is how the thermionic devices work, where you're using a heated filament to provide at least some of the energy required to get electrons to overcome the work function and leave the surface of the metal. The second way here, and this is what's being used in the diagram, is to use a voltage. And the third reason is due to the photoelectric effect, where we hit it with light of a sufficiently high frequency. And you can use any or all of these in any combination, as long as the total energy from either heat, voltage, light, or any or all of them put together is enough to overcome the work function. Then those electrons are going to become, those electrons are going to be ejected from the surface of the metal. Okay, now let's have a look at what this 4.1 volts thing is about. And like we said before, voltage is equal to work per unit of charge. Now, in this case, by providing the voltage, I'm giving these electrons some energy. And how much energy is that? So the energy in the work, which is the numerator of the fraction here, ends up being one and the same thing. So really, we're after the energy per charge, and in this case, we're not interested in coulombs, we're only interested in individual electrons. So really the formula becomes V is equal to E on QE. And we do have a value for V and we do have a value for QE because QE is constant. Okay, so let's substitute in here. I have 4.1 volts, 4.1 volts being equal to the energy and over QE, charge on the electron, negative 1.602 times 10 to the negative 19 coulombs here. Now, from now on, I'm going to ditch the negative sign off the front of the 1.602 because it's not needed, because it all becomes a scalar quantity. So we're now going to do our next line of working, where the energy is going to be equal to 4.1 volts times by 1.602 times 10 to the negative 19 coulombs. Okay, we multiply those two together and we get this value for energy here, and that is, by the time I put it through my calculator, it pops out at being 6.5682 times 10 to the negative 19 joules worth of energy. It's not much. Okay, why is this value here relevant? That depends on what's coming up next in the question, which is the graph. So we're just going to hold on to this value in the back of our minds for a second while we look at the graph. Now the graph is the tricky part, and if you don't understand what the graph is saying or how to interpret it, you're really not going to go much further with this question. Now what you will notice first up is that it is a graph of kinetic energy of photoelectrons that have been ejected from the surface of a metal against frequency. And typically when you see these sorts of diagrams, they look maybe something like this, where you've got the kinetic energy of photoelectrons, the frequency of light that's hitting the metal surface, and then you end up taking all these parallel sloped lines, and this might be for metal W, metal Y, metal Z, metal X, whatever. And at the point where these graphs meet the x-axis, where the kinetic energy of photoelectrons is 0, then that is representing where the threshold frequency is for that metal. Now, each metal, W, Y, Z, X, whatever, every metal is going to have its own unique threshold frequency, which is the minimum. Which is the minimum frequency of EMR that's required to eject electrons off the surface of the metal. Now, you'll see also that E is equal to HF. So if I then do this, where H is equal to E on F, E rise, F run, rise over run here, you'll see that you get a gradient H, which is the Planck constant. So every time you see these graphs, this is why for every metal, the gradient is constant, because it is the Planck constant. Now, this graph that you've been given is a little bit different, because the kinetic energy, instead of being in joules, is in electron volts. But that doesn't matter, because every single metal would still have the same gradient as that black line that we've got going here. Now, what's happening down at the origin? Because this here is the clue to everything. This means that when you have a frequency of 0 Hertz hitting that aluminium cathode or emitter in the photocell, when that frequency is 0, the kinetic energy is 0. But as soon as that frequency is anything other than 0, I'm getting kinetic energy of photoelectrons. Anything above 0 Hertz is ejecting photoelectrons from the surface of the metal. So that means that while I'm connected up to a voltage of 4.1 volts, I must be meeting the work function exactly. So this means that if I hold it at 4.1 volts and don't put any light on, then I don't get any photoelectrons, but any any photon of light that hits it now is going to be enough to cause ejection of those electrons from the metal surface. Okay. The final part of the question says this, and this is actually pretty confusing to read. It says the experiment is planned to be repeated using a voltage of 0 volts. Basically what this means is that in the photocell, they're going to remove that 4.1 volts altogether. So I'm not giving the electrons on the aluminium surface any additional energy. Okay, so the question is asking us to draw a line on the graph to show the predicted results of this planned experiment and determine the radiation frequency which would produce photoelectrons with a maximum kinetic energy of 1.2 electron volts using a voltage of 0 volts. What the hell does this mean? The first thing that we need to think about here is our initial voltage of 4.1 volts and what energy that represented. And if you recall, that means that at 4.1 volts we were meeting the work function, and 4.1 volts corresponded to an energy of, was it 6.566 times 10 to the negative 19 joules. That there is the work function, because that there was the energy for each electron that corresponded to 4.1 volts. Okay, so we need to now determine what the threshold frequency is. So I can do this by using the Planck relation E is equal to HF. Let's put it through. So this value here, okay, ooh, didn't mean to do that. What did we have? E is equal to HF, the energy value E, 6.566 times 10 to the negative 19 joules is equal to H, of course, is the Planck constant, 6.626 times 10 to the negative 34 joule seconds multiplied by the frequency. If I then solve for the frequency F, I get this value of 9.9 times 10 to the 14 hertz. Oops, why has that gone red? Times 10 to the 14 hertz. This means that a photon of light with this frequency will overcome the work function. So this means that that is the threshold frequency. And the threshold frequency always touches the x-axis. And let's change pen colors here. This is pretty much 10. So let's just, let's just put our dot there. Now, like I said, because the gradient of the graph here is always fixed, all lines here on these graphs are parallel, whether we're using energy in joules up here, which gives us a gradient of the Planck constant, or if we're using electron volts, doesn't matter. These gradient lines always end up being parallel to each other. So hopefully in your exam you've brought a ruler and you can simply just rule a line that's parallel to this one. And we're going to go up here, something like that. On the next slide, I will have ruled a straighter line, which we'll have a look at in a sec. Right, so I've fixed up the line there just to make it nice and straight. And like I said a second ago, all these lines have to have the same gradient because that's basically what happens with these kinetic energy of photoelectrons versus frequency graphs, whether that gradient is the Planck constant or something else. So now you can see that I've drawn this line there, and to address the remaining part of the question, which is to determine the radiation frequency that is going to produce photoelectrons with a maximum kinetic of 1.2 electron volts using a voltage of 0 volts. The first thing that we're going to do is we'll basically just read straight off the graph. So I'm going to put in a line across at 1.2 electron volts like so. Okay, and where that red line now hits my new line on the right there, I'm now going to drop down to the x-axis and read where it hits. Okay, and if you judge by the scale of the x-axis, each line is going up by an increment of 0.4, so we're pretty much going up by so we're pretty much going here and reading a value of 12.8, and remember it's times 10 to the 14 hertz, and that's your final answer. Okay. So there you have it. I said that this was a really, really terrible question. Very, very difficult. Once again, easy when you know how, but under exam conditions when you're stressed and not thinking clearly, picking your way through this problem is very, very difficult because it requires a number of assumptions to be made. So if you do end up with a question like this on exam day, good luck. I hope that you remember the process here, and hopefully you've also learnt something about electron volts that will clarify any situations where that concept is going to arise for you. Thanks for watching, and goodbye.